Hi, everyone, and welcome to another night of Astronomy on Tap in Kingston. We haven't had an event since October. I've just been too excited tuning into the JWST launch, watching it transform, and now cool down as it gets to start maybe taking pictures in about 6 or 8 weeks. But yeah, we're back. I hope you've been well. I'm Mark Richardson. I'm the Education and Outreach Officer for the Arthur B. McDonald Canadian Astroparticle Physics Research Institute. We're a collection of scientists, universities, and research labs across Canada, uncovering some of the biggest mysteries of the universe by looking at some of its smallest things. I'm here in Kingston, and I'm an astronomer and educator. So excited to hear from the different visitors that join us today, taking us on a tour of the different approaches to understand the cosmos. And I love taking these kinds of opportunities to bring a community together and revel in astronomy, a topic I think resonates with everyone, as like half of our world is the skies above us. These events are opportunities to share with you how amazing and exciting and useful science is in overcoming big problems. And I'm so happy people are able to join in live or after the fact. You know, this is staying on YouTube well after tonight. And so we're putting plans in motion too to maybe hold our next event, likely around early June, in person, where people will be able to join us still online and in person at the same time. So thanks again to everyone joining from home, wherever you are, wherever your homes are. So for me, I'm calling in from my home on the lands of the Cataraqui, now Kingston, the traditional land of the Anishinaabe and the Haudenosaunee peoples, and many Indigenous peoples before them. It's great that we're all able to learn tonight from our respective lands. My settler ancestors actually come from Scotland and France, and they came to Turtle Island through the process of colonialism. Myself, I was born in Halifax, Nova Scotia, the traditional Iskikowakak lands. In reflecting on the calls to action of the Truth and Reconciliation Report, I recognize the role of my ancestors in removing the stewards of those lands, and a similar story across a lot of Turtle Island. And as an astronomer, someone who revels in the wonder of the lands, the planet, the skies, and the universe, I recognize that this science relies on facilities that use traditional and sacred lands of various Indigenous peoples who have a voice to add to this science and who should be gatekeepers to these spaces. And so to all of you joining in, I urge you to think of the connection you have to the land around you, and the gift that we all have to learn wherever we are, including the access to dark skies above us. I have to say, made all the better right now because it is new moon, or I think actually yesterday was new moon. And so I'm also looking forward to the upcoming spring equinox and, more importantly, the spring weather. Of course, one of our speakers tonight already has the beautiful spring weather because she's not up here in Canada, but we'll get to her later. I also encourage you after tonight's event to explore the website whos.land. I have it linked here. It's a great resource. There's another one called native.land or native-land.ca. And they're really, really great resources for learning about the past peoples who have lived where you live. And so moving forward, let's reflect and work towards the decolonization of these spaces to make them ones of friendship, love, and access to all those in the community. Now, tonight's event is meant to be a conversation more than a lecture, so I hope you can chime in the YouTube comments with your questions. Certainly feel free to grab a drink, open your minds and imaginations, say hello from the comments, let us know where you're joining from, and do drop a question whenever you have one. I'll be here to facilitate taking those questions and asking the speakers. So today we're going to hear from 3 astronomers and physicists who all do very exciting but quite different research. And like always, we're going to have a little bit of trivia tonight, and there'll be some prizes available to you. And so to start us off, though, you know, it's been about 5 months since our last event. And if you've been tuning into these over and over, then you know that I like to always start off the night with a little bit of space news. And like I said, it's been 5 months. There's been some interesting space news, one of which I already hinted at today. But where would I begin without going back to our old friend, Perseverance? We've been spending a little bit of time off and on with our events, checking in with Perseverance. It's been just over a year since it landed on Mars, and I'm recognizing I have a typo on my slide. It should be a S, but we always like to nickname it Percy the rover. And so Percy first landed on Mars just over a year ago, yeah. And it had a bit of a rocky start to its sample collection mission. It turns out after drilling into the Martian surface to collect samples for possible missions, bringing this sample actually back to Earth, some of the debris that it was collecting actually fell into the fairing of the collection housing, and it wasn't able to actually reseal itself. So indeed, a rocky start. And it took some time, and of course, NASA had to figure out what to do with this. It is very far away from Earth. We can't just blow on it. And instead, they were able to do a little bit of maneuver, and they caught footage of kind of a before and after they did this maneuver to show what happened. And you see these rocks landed on the ground. So yay. And voila, the fairing is now clean. And so that sample is gonna be able to be stored properly. I also want to just maybe go back. What you can see here actually is the drill holes that Percy made in the ground. So that's where it actually took those samples. And those are going to be so important because kind of the future of some of the Mars missions is actually a sample return, right? So there's going to be 2 more missions kind of coming up in the future. So keep your eyes to Mars. One of which will come, collect the sample, and have kind of a rocket ready to bring that up into space. And then that actually has to meet another mission that will be launched from Earth to Mars to actually capture that kind of capsule and then bring it back here to Earth so we can do some proper samples or a proper study of a sample taken from Mars. So this is really like what Percy's doing right now is step 1 in a very multi-year process. I think current plans are maybe that journey leaving Earth, going to Mars to pick up that final sample will be around 2026. So this is a long time coming, but we're getting there. But yes, one problem solved, and it didn't even need Mark Watney there at all. Indeed, now that we're getting closer and closer to allowing us to be able to transfer material from here and Mars, I think it's safe for Matt Damon to indeed go to space. He's always seems to have to be rescued when he does. Anyway, moving on, of course, some other big news this past 5 months is since we last spoke, JWST finally launched, and this was after years and years of delays. So I think like comics like XKCD will have to admit they extrapolated poorly. They were thinking maybe at the rate it was being delayed, it would finally launch in 2026. No, it launched in 2021, Christmas morning, yeah, it had a basically flawless launch. I have to say it's the first time in a long time I woke up extra early on Christmas. I like my sleep, and Christmas is no exception, but I got up to watch that launch live. And the footage was just fantastic. If you tuned in, you know, there was amazing footage from the actual rocket that took it up to space. And once it was there was actually footage of the satellite itself coming off the kind of rocket stage. And by allowing this kind of footage to be captured, they were able to see even some of the following steps. Now, like I said, JWST doesn't go up in the rocket ready to observe. And we heard all about that actually back in October from one of our speakers, Lamia Mullah. Instead, it had this whole process, right, of basically 13 or so days of setting up all the different processing that it needed to do to unfold itself from being within the rocket capsule. And indeed, and of course, I've maybe planned this just wrong, you should be able to see one of these stages actually happen any moment here. There we go. I thought it was lagging up. And as it went out, it was really neat because originally this was supposed to happen 30 minutes into the mission, but because there was almost no spin happening with the satellite after it disengaged from the rocket, they were able to do the very first thing that happened in this video, which is extend the solar panels while it was still on kind of camera, which was really, really crucial in case anything happened wrong when that went down. But over 13 days, it continued to expand, basically opening up its sun shield, becoming a fully functional telescope. This is going a little bit slower than I planned. I think my computer's struggling with this. I won't linger too long. But yeah, indeed, a month later after this whole process, it arrived at the location of the second Lagrange point of the Earth-Sun system. And that's where it's going to keep kind of put in its orbit. And there, its main goal is to shed light on our cosmic origins. It's going to observe the universe's first galaxies that formed right after, shortly after the Big Bang. It's going to reveal maybe the birth of stars and planets, and we're going to hear a talk tonight that ties into that a little bit. And it's going to look for planets around other stars with the potential for life. And indeed, there's other facilities that will be trying to help JWST in that mission, and a different talk tonight might tie into that. Of course, JWST is still cooling down now. You can go to Where is Web. You can search that and find out what its current state is. It's at like minus 230 degrees, which means it's almost ready to maybe start being able to take proper pictures. It is an infrared camera for the most part, and so it emits its own light. And so if it's not cool enough, then it can actually shine on its sensors. But we're already starting to get some checks on the optics in it, and we're able to see that indeed all the mirrors in the telescope are working correctly and able to focus that telescope. And so early calibrations happening now. Some of the more instrumental calibrations going to start in the next 8 weeks, I think. So I'm really looking forward to this. And of course, I think everybody was so worried there's something going wrong on the launch. It went flawlessly. And last but not least, I wanted to take a moment to maybe talk about the sun, the light in the sky, and just highlight that solar activity is totally picking up now. We are approaching kind of solar maximum, and so I thought I would highlight that this sun, as it gets a little bit more active, it can have impacts on technology here on Earth. Now, the sun follows an 11-year cycle where each cycle, the magnetic field of the sun basically completely flips direction. And in this time, the sun goes from being quiet with basically no sunspots. If you have a solar telescope, you get to look at it and it's just very, very boring, to the more exciting times like right now, where it's becoming active, where there's lots of sunspots. And so we're now kind of getting well into that active time. There's lots of sunspots. This is a picture of the sun from today. And this activity is, of course, leading to a little bit more outflows and winds. So these sunspots and the sun's magnetic fields, they can launch these large outflows, like you see one coming out here. And these can be launched through the solar system and sometimes even towards the Earth, these coronal mass ejections. And if they hit the Earth, they can actually affect the electronics in our satellites and even affect the power grid here on Earth. If you're familiar with the March 1989 power outage, which was related to one of these events. Now, this can actually have really, really true impacts. This is something that came about just last month. It turns out SpaceX's Starlink satellites were affected by a geomagnetic storm, which is where the winds from the solar flare actually interact with the Earth's magnetic field. And this can then, again, impact electronics. And it happened at the same time that SpaceX was launching a number of their Starlink satellites. And apparently dozens of the SpaceX Starlink satellites actually were affected. And it was affected while they're actually being deployed. And the result was they actually fell back to Earth. And so you can see some videos from, I think, the Caribbean of these falling back into the Earth and burning up. So definitely a different type of meteor shower that some people were privileged to. But yeah, so something to think about a little bit, because of course, as the sun becomes more active, with any luck, maybe we get some of those northern lights come a little bit further south in Canada, maybe into the US. And I always like those opportunities. Of course, this picture, beautiful picture, was taken in, I think, in Yellowknife. And so, with any luck, something that phenomenal will be visible here in Kingston. But yeah, so that's kind of the space news I wanted to highlight for now. Of course, we're going to have some more updates when we have our next Astronomy on Tap, but I want to then move forward on to the main event. And so to begin our night, our first speaker is Arnaud Michel. And so Arnaud, I don't know if you want to show your camera. Arnaud is curious about the world and keen to have fun. He likes being outside, whether it's minus 20 or positive 30 Celsius. And he goes outside to ski, to climb, to surf. Arnaud likes dust when it's around young stars, but not so much when it's on his rock climbing holds. Here at Queen's, he's a master's student with Professor Sarah Sadavoy. He is studying protoplanetary disks, and he enjoys opportunities like tonight, as he is also eager to change the world for the better in a variety of small ways. Speaking of which, actually, Arnaud says he wanted his fun fact to share with everybody is that he thinks The Invisible Woman by Carolyn Criado Perez is a book that everyone should read, and so I'm going to be adding that to my list. But without any further ado, Arnaud, if you want to take over and share your screen, then I would love to hear from you.
Thank you very much, Mark. So hello, everyone. My name is Arnaud, as Mark has mentioned, and so today I'll be speaking to you a bit about how planets are forged in dusty frisbees. And so here we have a nice artistic rendition of what that could look like. And so here you can imagine there's a central star, and then a dusty frisbee was the object of interest here being the planet that is being formed. But before jumping too deep, let's think about where we are. We're on Earth. We can see it. It's everywhere around us. This is a slightly different angle, obviously. This is not what we see every day, but generally, we're pretty sure it's here. And so we always, humanity has often asked deep questions of where do we come from and so on. And I think there's a foundational question under there, is that where do we come from can only exist if there is a planet on which life can develop. And so this kind of paves my idea of why this is interesting as to philosophically describing planet formation. And so planets, as you might already know, come in all sorts of shapes. In our own solar system, we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Neptune, Uranus. And so all within our own solar system, there's a wide diversity, from very dry and hot planets like in Mercury to gaseous giants like Jupiter. And so we can see that in this story I'm going to try and craft about planet formation, this process has to be able to make a wide range of different planets. When we look out at the exoplanets, those are planets around other stars than the sun, the diversity balloons even to greater magnitudes, where there's planets that are 10 times the size of Jupiter, planets orbiting 2 stars, or even reports of where planets have molten iron raining onto the surface. And so this even complicates further of trying to find a theory and a description of how planets are formed. So where are they formed? So I mentioned frisbees. This is a frisbee, but not the one we're looking for. There's another frisbee being caught by a cute dog. But the frisbee we're looking for is this one, a protoplanetary disk. And so this is HL Tau. It's the first high resolution observation of one of these dusty frisbees. And so I've been talking about dusty frisbees a lot. And so that is because this image of HL Tau is an image of dust. And so we're explaining these frisbees as being entirely made up of dust and some gas. I'll be focusing on the dust today. And so while there was this first amazing image in 2014, over the past 8 years, we've expanded our view and we've discovered a whole wide range of types of disks, of different disk sizes with different properties ranging from rings to gaps. In some of them, there's spirals. In some of them, there's more dust on one side, less on the other. And so this kind of leads this question of we have plenty of disks. We observe plenty of exoplanets. So what is the bridge? And so our idea is that this dust will form the planets. But how so? And how do we find this dust to start out? So there's this telescope, this observatory in Chile called the Atacama Large Millimeter Array, ALMA for short, that looks specifically and only actually at small millimeter sized dust as well as gas. But in this context, it looks specifically at dust. And the physics behind it is that small dust that's 1 millimeter in size will emit light at a 1 millimeter wavelength. And so with this telescope, we can observe all our dusty frisbees. And so speaking of sand, by now you might have noticed that I'm speaking about dust and it's really small. And this is where the real challenge comes in. How do you get dust to form a whole planet, which as far as we can tell is pretty solid. And we're pretty sure that most planets either are solid, or some of them have liquid molten surfaces, but generally we're going from dust to a solid mass. And so this is where the big question really lies, as to having a theory and a description of this transition from the dust we observe to the exoplanets we observe. And so generally, we can explain this quite simply as a process of making a snowball. Think of the snowflakes as the dust. And so you go down, you grab your snowflakes, you smush them together in your hand, and you compact it, and then you've got a solid snowball. And so this is, to a very simplified extent, what we think could be happening in these protoplanetary disks, where dust is coming together and through a variety of forces getting smushed together to form a planet. The catch is, as you might know, when it's, for example, too cold, it's really hard to make a snowball. It just doesn't stick together. And so similarly, in these dusty frisbees, it can be, we think it could be really hard to get the dust to stick together. And so this starts to like dive into the question of like, how is it exactly, and where is it in these dusty frisbees that the dust will actually stick and not break apart? And so we have some ideas. And amongst them is that once you form a big enough small dust particle, there's a bit of a snowball effect, literally, where it continues to grab on extra dust and it becomes larger and larger. And so now we have a bunch of guys trying to make it maybe the biggest snowball in the world. But what I really want to draw your attention to is that as they're rolling the snowball, behind them, there's a track of grass. And so if you've made a snowman, you've probably noticed that too. After you've rolled your snowman, behind you, you leave a trail where there's no more snow. In this case, we think that the similar process could be happening in some of these disks, where a planet is actually potentially sitting in one of these gaps between the rings, having cleared out this region of dust. And so we can't see it in these images because we're looking at the millimeter-sized dust. And so if the planet's a big object, it just doesn't show up. However, that's one of the explanations as to the formation of planets and their location in these types of disks. And then becomes a question of how does a planet impact the dusty disk, and so on. And so conceptually, in terms of the artistic rendition, this is really what's happening. Here we can see the planet because it's a drawing. And so it's sweeping up all the material and hindering further material from coming in. And so in that sense, you have over time, all this dust being swept into this planet and then further planets being formed further out, such that over time, you've got yourself a star and a planetary system around it. And so it's this jump that is really at the forefront of our attempt to describe planet formation. Because as I've mentioned, we've got disks and we've got exoplanets. And we've actually got one instance where we have what we think is both. In this image of PDS-70, we have a big disk. It's called a particular transition disk due to the big gap in the center where the star would be located right here, where my cursor is. And at the two locations indicated by these arrows, PDS-70b right here and PDS-70c right here, there's a bit of excess and very localized dust emission. And through a variety of constraints and models, the astronomers think that this is the first evidence of baby planets forming within one of these protoplanetary disks. So lending this idea that these planets are clearing out this area of this dusty frisbee. And so in that sense, we've got like what we think is like the answer. However, there's a catch. We have this one example, but we have many, many disks and many, many exoplanets, but few observations that bridge these two steps. We have theories and computational models that do this quite well, where you give it a series of these disks, for example, not just these 6, but like hundreds, and then you run them for a while, and then you retrieve a variety of exoplanets. And that's really both challenging in terms of making sure that that actually works out physically, but that's all nice and good, but we'd like confirmation, just as we saw in PDS-70, where we have the two little blobs that we can say, okay, those are planets. So there's a real search right now going on, and future telescope development that's like really at the forefront of trying to build instruments that can find evidence of planets in these rings. Because as I mentioned early on, we'd like it to be planets. We know that planets should form somewhere, but there's an entirely other range of scenarios where just the physics can induce gap and ring formation. But that's a little less exciting. We like to think that it could be planets. And so now it remains to confirm that. So looking ahead, we have two nice telescopes that will help do that. One of them, as Mark mentioned, is a James Webb Space Telescope that just recently launched that will be able to precisely characterize very young planets and hopefully, potentially in some cases, find them within the disks. But the main focus with the James Webb will be really to find young planets and try to study their properties and where they are in relation to the star, and then try to infer some of its history. But then further towards the end of this decade, looking at the Nancy Grace Roman Space Telescope, this is a space telescope that will directly be able to image the exoplanet within like protoplanetary disks, within those gaps, if there are any. I think that's the biggest caveat. So current campaigns are really under development, and I think this is an exciting avenue where we've got evidence of disks, evidence of exoplanets, and we're just trying to bridge them together to describe how planets form. And that will be all.
Thank you, Arnaud. That's really, really fascinating and just so exciting how this is like really on like our doorstep, and that it's like this JWST first and then even the Roman Space Telescope. I mean, it's not that far away. And so more data is always going to be so exciting. So thank you again for a great talk. We've had a number of questions come in. Sean was asking, he almost made a comment that ties into a question. Maybe we'll start with my question, because I think it ties into what Sean's question is as well. So in your snowball example, you had us to go in and put our hands into the snow and bring it together. And so my question is, for the dust, what's kind of the forces that are doing that clumping instead? What's replacing the human in the analogy?
Right. So these dusty frisbees that we have here are rotating around their host star. And so a bit like a frisbee, when you throw it, it can rotate on its own. And so the dust within it is pulled outwards, but then the gravity of the star is also pulling the dust inwards. And so there's, to some extent, a balance of these forces. Generally, some of them will one of the forces will be overcome. Early on in the disk lifetime, the dust will fall inwards as it grows, it will fall even further inwards. So it's spinning into the center of the star. And so any small disturbance in these dusty disks, these dusty frisbees, can cause, for example, a small block at some point and an instability often. And so at that point, your dust really starts that snowballing effect where gravity, the particle becomes big enough that it starts to pull in other small dust grains around it. And then you get really the snowball effect where dust really agglomerates. And once you formed your first planet, that's really where it's a trigger to further planet formation. As you form your first planet, we expect maybe that it starts to clear out a region, and therefore the dust that's further out can't just fall in, and so it accumulates in rings. And so then you've got a lot of dust really close together, and a bit like an instability is really easy to trigger the clumping through gravity. So gravity is really like that force that brings things together.
Mm-hmm. Yeah, I think that ties into a point that Sean was saying, that this seems to be like a runaway process. As soon as you have that little bit of instability, there's more stuff there. So I guess the gravity kind of runs away on that, and so it grows faster and more.
Exactly. That's why I like the snowball. It just keeps going.
And another question from Sean was, what role, well, I guess you spoke to that a little bit specifically. He asked it kind of in the middle of the talk, but maybe specifically he was wondering, what role will JWST play in planet hunting?
So as far as I know, and then there's always a catch. It's a new telescope. It'll probably do a lot more than we're expecting, which is really awesome. But the current programs that are really looking at exoplanets are trying to precisely describe what's the composition of the atmospheres around exoplanets. So trying to determine what there is. We have good constraints on our own atmosphere on Earth. We have some good constraints in our solar system, but JWST will do this for a variety of exoplanets. And with this distribution across many systems, you can start making inferences as to where it was formed, maybe in the initial dusty frisbee within the initial disk, and what happened. So that's the first step. I guess we'll see soon enough how much more there really is once we're surprised.
Sean had a follow-up, which is like, if you're sampling the atmosphere, would you maybe be able to see signs of civilization?
So that's a good question.
Industry?
So it goes both ways, in the sense that if you believe there is no other method beyond some geological or biological way to create a particular element in a large enough abundance, you can make a compelling case that it could be a life form that is causing this gas, or the presence of this gas. But the one catch is that we're going to be looking, because far away, everything in space is far away. And so we're looking back in time. And so say someone out there in our galaxy points their telescopes on Earth and looks very precisely and can disentangle what is in the atmosphere. They would be looking at the Earth maybe thousands of years ago, or maybe 1 million years ago, at which point the effect of humans, at least, on the atmosphere is to a great extent negligible. So I think it's a very tricky question as to saying, we can see something, but is it now or was it in the past?
Interesting. Just a reminder, everybody, you can put any questions you have for Arnaud or for any of our future speakers in the comments in YouTube, and we'll bring them into this space. Another question for you was a little bit more details about the dust particles. Like, what are they? What are they made of? What are their sizes?
Yeah, I think dust is literally the answer. It actually is dust, sand. It really is sand. It's silicates, it's carbons, it's actually sand. It's sand grains. And how big are they? Actually, the same distribution as sand. Sand can go from 1 millimeter to a couple microns, very fine sand. So if you go to a beach where it's like kind of coarse, that's like on the bigger edge of what we can observe. And if you go to a beach where it's like very fine sand and dusty-like, that's how small it can get in our observations of these, specifically these dusty frisbees I've been showing. But yeah, sand is a really good analogy.
And my question was, so the gaps are made in the beautiful pictures you have from ALMA. That's where we believe planets have basically, all that dust has accumulated into a planet. And then you have these rings that's like difficult to come in, as you described. Is the expectation that that ring will form another planet in the future, or will it eventually settle on to one of the planets that has probably already been made?
So if the ring is massive enough, it's likely you could have second generation planets. And so this is where the diversity of planets really links with the diversity of disks, where the planets are the size of Jupiter or larger. Given the masses that we've been able to infer for these rings, there just isn't enough dust. But there is enough dust to form a planet like Earth, with the mass of Earth, for example, in some cases. And so you could definitely have further planet formation. So it's not just everything happens at the start and then there's nothing left. You can have a sequential induced planet formation.
Really?
And so then you have so many different planets.
Yeah, no, that's fascinating. I think that's it for questions for now. We need to move on to our first round of trivia. Arnaud, I want to really thank you again for giving an excellent talk. And I know we'll have you back at the end in case there's any last minute questions for you, or maybe some of our other speakers have questions for you. And so that'll be an opportunity to talk a little bit more about that. But for now, thanks again and see you in a bit. And I'm going to share my screen. I think. Can everybody see that? Well, then we're on to the first round of trivia. So in the description of the YouTube video, you should see this link. You can click on it, or if you have a separate device, you can put bit.ly/AOT-MR3, so March 3rd, MAR3-trivia. And that should open up a place where you can start putting your answers to the rounds of trivia. Again, we will be giving away 2 prizes, one for the highest score, and one is just kind of drawn from everybody that submits an answer. So even if you don't do very well at trivia, even if my helper, Nick, who's in the background today, made a very hard round of trivia for all of you, you still have a shot at a prize. So do submit your answers, even if they're all wrong. The whole point is, but please don't reveal to anybody publicly. Don't put it in the YouTube chat. You need to be putting it in the Google form that is linked in at this link on the screen here, or in the description of the YouTube. There's a link there where you can go to the form. But again, please do not spoil the answers. And we will cut this off at the end of today so that we can find our winners. But without any more ado, let's start the trivia, which is with some maybe a little bit easier questions. Which is larger, Neptune or Saturn? Of the 2 planets, Neptune or Saturn, and not the Roman gods, but of the planets themselves, which is larger, Neptune or Saturn? It's question 1. And I will repeat every question. Question 2, where is the Oort cloud located? Is it in your coffee in the morning? Is it over South America, North America, or is it maybe something a little bit more astronomical? Question number 3. What is the sun's outermost atmosphere called? And if you're paying attention to space news, you might have heard the word. Spoiler alert. So question number 3, what is the sun's outermost atmosphere called? Okay, question number 4, name the scientist. Who's this guy here? Who is that person? All right, and last but not least, the last question of round 1, question number 5, it was, what is the farthest distance from Earth that a manned mission, or in other words, a person, a human, has ever traveled from the Earth? What distance? And we have quite a big allowance. We'll be open to a few values. You don't need to be bang on. So roughly be within about 20, I'll probably even be a little bit more lenient, 20,000 miles. Yeah, or what's that, like 35,000 kilometers or so. So about a third of 100,000 kilometers. That's kind of the range we'll give. All right, one last time. Remember, you can put your answers in at this form, which again, there's a link to it in the description of YouTube. Question 1, which is the larger planet, Neptune or Saturn? Just give the name for the larger planet. Which is larger, Neptune or Saturn? Question number 2, where is the Oort cloud located? Where can you find the Oort cloud? You know, something else that's happened in the last 5 months is Wordle has exploded. We need to start making some astronomical Wordles that we throw into the trivia, I think. Question number 3, what is the sun's outermost atmosphere called? And I believe, actually, another little bit of space news. I think in the last 5 months, there was a spacecraft, maybe I'll look it up before I come back to you. But yeah, there's a spacecraft that got to actually fly through this bit of the outermost atmosphere. Question number 4, name the scientist. Who is this person? And last but not least, what is the farthest distance from Earth a manned mission has traveled within about 35,000 kilometers or 20,000 miles? And my helpful helpers in the background tell me it was the Parker Solar Probe is what went through that atmosphere. So that really, you know, if you watch Star Trek Next Generation, they go a little bit deeper when Beverly Crusher wants to go into the sun, but Parker Probe did pretty good too, went into the outermost atmosphere of our sun. Really sampled this energetic area, right, where those solar winds and whatnot are coming from. Okay, that's it for round 1 of trivia. So just hold on to that Google form. We'll come back for round 2 to fill in the next 5 questions before you can submit them. But I want to go on to our next speaker. And so to do something a little bit different, actually, I'm going to invite a familiar face from Astronomy on Tap and the scientific director of the McDonald Institute. I'm going to introduce Tony first to actually then introduce our next speaker because, well, he's going to tell you, but my understanding is that Tony is a past graduate supervisor of our next speaker. And so, Tony, I'm gonna hand the floor to you to introduce Alvine.
Great, thanks, Mark. And I'm certainly going to enjoy introducing Alvine. So as Mark said, Alvine and I go back a little way. Alvine's career actually started before she came to Canada. She did her bachelor's degree and a master's degree in theory at Douala in her native Cameroon, and went on to, I guess she was exploring theory for a while. She went on to do a master's in Italy before she saw the light and decided that experimental physics was the right thing to do. I think she had met Art McDonald, got excited about what we were doing at Queen's, and applied to Queen's and joined me as a graduate student. I still remember the first day that I met Alvine. She was starting in September. It was middle to late August, and we were having one of those heat waves where it was sort of 30 degrees and the paint was peeling off the walls of my office. And she came in and asked, is it always this cold here? And so she had some surprises coming up. I remember we took her to Montreal and she simply could not physically leave the building because the temperature in Montreal was so blisteringly cold. But she stuck through it and she stuck with me, stuck through that as well. And she got her PhD in 2015 working on a dark matter experiment called Picasso, and then moving on to another one called Pico as a postdoc. She then went and joined another group on News G, still pursuing the dark matter thing. Eventually got tired of the cold in Canada and decided to move south. So she moved only a little bit though, and she moved to Albany, where she did a postdoc working again on dark matter, this time with an experiment called LZ. Finally realized that wasn't far enough and has now just taken up a new professorship. So she's actually a chair position, an endowed chair, the Terasaki Endowed Chair in Physical Sciences at UCLA. And she started building a group there to work on dark matter. She's working still on the LZ experiment, but also trying to develop other technologies for looking at dark matter. And on top of that, she's also very passionate about developing opportunities for STEM, for students that are underprivileged or have been misrepresented, if you like, in the community. And so that's an area of activity for her as well. So Alvine, welcome back. It's been a long time since we've seen you. So I'm delighted to see you again and to hear what you have to say.
Thank you very much, Tony, for the introduction. I had bet with my husband that you were going to talk about the weather story when we first met.
I decided to leave out the snake story.
Hi, everyone. Thank you for tuning in today. It's my pleasure to be back. And actually, it's my pleasure to be here today talking about a very fantastic topic in physics, which is basically hunting for the missing matter of the universe as a way to put together the puzzle that will help us to better understand our universe and its fate. So today I'll be talking about dark matter, searching for the dark matter. And the story to start The story goes back to the 1930s when astronomers started to study the dynamic of galaxies, and they discovered that the galaxies were rotating too fast, that if you were to infer the gravitational mass of the galaxies based on their rotation, you were going to get a larger mass than the actual mass of the galaxies if you were to base on their visible content. So that led to numerous other evidences for the dark matter case to be collected. And today we have so many other evidences for dark matter. And on this slide, I'm showing a very simple one. And what you see right now on this slide is basically the speed of the stars within the galaxy, the center of the galaxy, and also at the edge of a galaxy called spiral galaxy. So you can see those two arms, and you can see, focusing on the right-hand side, which shows the picture of the universe with dark matter, that the stars at the edge of the galaxy are rotating too fast, that if there was no dark matter halo around the edge of the galaxy to keep those stars gravitationally bound, they will fly out of the galaxy. So basically the dark matter evidences collected so far are mostly from gravitation, and they can be thought of as the wind. You don't see the wind, but you see the effect of the wind. The same thing is as of with the dark matter. We don't see dark matter, but we see its effect on different astronomical scales. And one of the other evidences of dark matter has led to an astonishing conclusion. It was shown from an evidence studying basically some ancient light in the universe called CMB, or cosmic microwave background, that the universe as we know it is not as we see it. So basically what we can see, meaning you and I and all the structures we can see, the fancy tablet that you are using right now to tune into this YouTube video, is only 4.6% of the universe, and of the universe in total. And there is 85% of the mass of the universe that is missing and is invisible. So that is the so-called dark matter we are actively trying to look for right now. And I'm sure that at this moment, so many questions can be going through your mind. You can be thinking, then what is the invisible or the dark matter of the universe made of? How does it interact? Then we know the 4 different types of interaction that normal particles go through. Should dark matter interact that way, or is there any other type of interaction? Basically focus on dark matter particles, and how do we go about then searching for something like dark matter that is invisible? And mostly also, why do we care about searching for the invisible dark matter? And of course, many other questions that I'm sure you are going to post on the chat. It is going to be my pleasure to answer. So I'm going to be focusing on those 4 only, and I will be dividing them throughout the rest of my presentation tonight. So let us start with what is not dark matter. Dark matter is not made of any other particles that we are familiar with. Like for instance, photons from the light in your room right now, or electrons or protons or neutrons, anything we are familiar with, so-called standard model particles. Dark matter is not made out of those particles, because those particles to some extent interact with light. And because they interact with light, if dark matter was made out of those particles, we could have used an optical means to be able to detect dark matter. So we know for sure that dark matter is not made out of those particles. But then what is exactly the dark matter particle? That is still a question that we are unable to answer at this moment, but we have a wide field of candidates, as you can see on this picture portrayed here, from theory. Theoretical model give us so many different candidates for dark matter, and as experimental physicists like myself, we are going through carefully and strategically through all those different dark matter particle candidates to try to rule out some of them or confirm some of them as potential dark matter. And the way we do that via 3 different means. One of the way is very simple. We have colliders experiment like the LHC that discovered the Higgs boson a few summers ago, where normally we just take 2 beams of high energy particles that we are used to, for instance, protons, and collide them at the center of the detector, portrayed here in the bottom right. And by colliding them like that, there will be some product from the collision of those 2 particles. And we are hoping then that if there was any missing energy from the collision of those two particle colliding, 2 beam of particle colliding together, then the missing energy could be inferred to the dark matter. Because the dark matter is not visible, you are not going to see the dark matter in your detector, but you are going to see, for instance, a missing energy that will be an inference to the dark matter detection. This is method one. And another method is to look out in the space, to basically send space missions like AMS from NASA, where they look basically at given strategic region of space where there might be an abundance of dark matter particles based on some theoretical model. And if dark matter happens to be its own antiparticle, where they are overdense a population of dark matter, they may annihilate, as they will, there will be a bunch of them in that dense region of the space. They may annihilate and produce an excess of standard model particle we are used to. Then having an excess of maybe electron or positron in a region of the space where we know we should not have that excess can be an indirect inference of the dark matter existence in that location of the space. A third method, which is what I work on, is basically trying to detect dark matter through an atomic billiard game type collision reaction in underground detector. So basically you have a huge detector sitting in an underground space, and the atoms of the detector are originally at rest. Dark matter particle coming in your detector will scatter with those atoms originally at rest and infer some energy to those particles. Then the energy that is deposited by dark matter that will create the recall of those particles might produce a phase transition in your detector. So a detector originally at rest may suddenly produce light, or may produce heat, or may produce charge from the recalling interaction in your detector. So picking up then, having a detector that is sensitive to either one of those three phase transition, either heat, either light, either charge, will be a direct inference of a dark matter elastic scattering inside the detector. And what I have shown here on this slide is basically trying to highlight two great experiments at Queen's University I have worked on. Tony just spoke about them, the Picasso, which later on became the Pico experiment, and the News G experiment. And right now I'm currently working on a detector called LZ, which is the biggest and cleanest type of detector in its own category. That basically, instead of being like Picasso or News G, for instance, looking only at one of those three different phase transition, LZ combines two of those phase transition inside the detector. And the more phase transition you succeed in combining inside the detector, it gives you more sensitivity to reject what is not dark matter compared to what might be dark matter. So those phase transition happens if they were due to dark matter, maybe at the level of, let's say, one event per tons of kilogram of the tons of target material of the detector per maybe 10 years. While other particles that we are so used to, like for instance, the high energetic cosmic ray or the natural radioactivity from everything that surrounds us, including the air we breathe, producing all kinds of particles like electrons, photons, and so forth, will interact and may also produce those type of phase transition at the level of maybe billion events per second in a detector, per ton of target material in the detector. So if you quickly do the math, you will understand then that dark matter search gets a little bit complicated. Instead of being a vanilla story where we know we are trying to detect one of the three phase transition in the super quiet atmosphere, we are trying to detect one of those three phase transitions in an atmosphere where everything surrounding the detector is producing so many background in the detector. I have put this funny picture here just to show that dark matter search is basically looking for a needle in the haystack, where the haystack is basically the interaction or the phase transition produced by all the other particles surrounding the detector, and the needle is the dark matter you are looking for. So the main goal then for any dark matter search based on an underground detector is to reduce those background, and there are various strategies, and one of them is basically going underground. You can go in an underground lab like the Snow Lab in Sudbury, or you can go in an underground lab like the Sanford Underground Research Facility in the US, where my experiment is currently located. And the reason being is that you want to use the rock overburden above your laboratory to help shielding most of the cosmic ray. that will have otherwise swamp your detector and produce that needle in the haystack type scenario. So once you do that, you succeed in reducing some of the haystack, but you still remain with some of them as well. So then you move to the second strategy. The second strategy, which we have developed very thoroughly during the construction of the detector I'm currently working on, is to make sure that, as we know that everything is radioactive, I am radioactive, you are as well. The computer we use is radioactive. Anything basically is radioactive. So what we try to do during the LZ detector construction is to make sure that from all the materials that we use to assemble our detectors, we were thoroughly screening those materials, or mainly measuring the radioactivity from those materials, ensuring that we select the best grade of any given material we wanted for the detector that has the lowest radioactivity, and build the detector under the cleanest condition possible. We basically build the LZ detector in one of those special rooms that have a very reduced dust content and a very reduced radon content to avoid dust or radon, which are radioactive, to plate into the surface of the detector and later on also produce some of the hay in the haystack. So the third strategy then, once you have gone underground, you have selected the best radio pure material to be the detector, is to surround the detector or the heart of your detector with massive shielding. And I'm showing here two experiments, CAD drawing with the shielding. And what you can see on the left is basically the LZ detector, where you can see that we have layers of shielding surrounding the core of the detector, which is quite small compared to the whole shielding. And the reason being, again, is that atomic beer ball collision reaction happening. Any background that we come will interfere with the shielding material and will be moderated or stopped before coming into the heart of the detector. And on the right is basically a CAD drawing from the NEWS-D detector, where you can see again layers of different materials like polyethylene and lead surrounding the heart of the detector to reduce those backgrounds. So those three different strategies are what we use in dark matter. And of course, there are more strategies, but those are the three main ones that we use. And after that, then we turn on the detector, we collect the data, and at the end of the day, we analyze those data and see if there is any evidence for dark matter discovery inside of those detectors. At this point, I'm sure that in your mind, then the next question is, have you found an evidence for dark matter detector, for dark matter discovery in your detector? And the answer here in pink is no, we haven't found it yet. But as you can see from this plot here, we have spent decades thoroughly searching for dark matter and constantly excluding some of the region, and then we believe that we are drawing closer and closer to a discovery. And as I said, for instance, the LZ experiment has been built, is the cleanest and then the biggest one, and it has turned on, and we perhaps show some result for dark matter search this year or next year, and those results promise to be exciting, so stay tuned. So then let's say LZ finds dark matter, or any other experiment like PICO, for instance, or NEWS-D found dark matter. What does come next? What comes next if dark matter is found is to study the property of dark matter and then answer the two first questions I have asked on the slide earlier on. What is the nature of the dark matter particle? What are the type of interaction a dark matter particle undergo with a normal particle we are used to? Now, the next question is about why do we care about searching for the invisible? I'm going to leave it in backup slide because of time, and I'm hoping someone in the audience will ask question and I will be able to answer that. So I will stop here. Thank you.
Thanks, Alvine. That was a great talk, and just a really good overview of like all the different parts that you need to put into kind of your hunting apparatus for dark matter. So yes, indeed, do ask your questions in the chat. I think Alvine even did some work for you and let you know what a really good question would be if you want to see a few more slides. But to begin with, actually, at the very beginning of your talk, when you were talking about kind of the rotation curves of galaxies, One person asked, do the supermassive black holes at the center of the galaxy, do they play a big kind of gravitational role in holding galaxies together or not?
That's an excellent question. So supermassive black hole will play a role in holding the galaxy together, but not, they need to be more massive or more dense at the level of the dark matter density we are looking for to be able to play that role that dark matter plays. I'm sure that the person, or I think the person who asked that question was coming from the fact that initially when we discovered dark matter, we started thinking that perhaps dark matter may be some supermassive black hole, right? That because they interact very feebly with light, they look at that time as potential dark matter candidate. And it turned out that by discovering supermassive black hole and studying jet density and so forth, they were not dense enough to make up the amount of dark matter we need to impact galaxies' rotation at the level at which dark matter impacts them. So I'm going to say yes, supermassive black holes do play a role in holding the galaxy together, but not as much as dark matter. That's why they were ruled out as a potential dark matter candidate.
Very interesting. Another question I had was, you showed the picture of the standard model of particles, and you said, yeah, but it can't be any of these. They interact with light, and we know that it doesn't interact with light. But the exception to that, right, is the neutrinos. And so I'm curious to know, how do we know that dark matter is not neutrinos?
Very good question. So I'm going to answer and then the short one. I'm going to start with the very long one. The story of dark matter, basically when we discovered that there was some missing mass in the universe, we tried to trace it back to the Big Bang, right? To how the structures evolve after the Big Bang. And we discovered that when dark matter, like if you study the galaxy formation and the structure formation from the Big Bang using dark matter, the way those galaxies form together, where light nuclei started to attract each other and then building upon like that, that snowball rolling effect to form the galaxies we have today. If the dark matter were not massive, or when we're not moving at a very slow speed to allow that formation of structure, then the universe as we know it today will not be as we know it. So the size of the structure, like that, the galactic structure that have been formed today will not be as big as they are today. So let's take the instance, the example of the neutrino, for instance. Neutrinos are relativistic particles, right? Meaning that they speed too fast or they move too fast. Those particles moving too fast will have been bouncing off matter, forbidding them or hindering them from forming, from gravitationally pulling on each other to form bigger and bigger and bigger structure. So that is why basically neutrinos as the sole dark matter candidate has been ruled out. But there is still possibility that not those three neutrinos shown in the standard model, like electron neutrino, muon neutrino, or tau neutrino, but a different type of neutrino called sterile neutrinos that is slightly more massive could be a potential dark matter candidate. Just
suddenly worried that that's going to really affect the aesthetics of this table, but if another neutrino has to be added, but I'm sure that that particle physicists will have no problem adapting the table to look pretty.
Yeah. And then the short answer, I said I was going to give you two answers. And then the short answer again is the density thing. Is the density density answer. For the density of the neutrinos, for the neutrinos, because they are very tiny in mass, for the amount of them that we know to be out there to make up the density of dark matter, there will be a discrepancy. We need a factor of so many orders of magnitude more neutrinos that we currently know they are to make up the dark matter density. So it's still the density problem, like with black holes.
That's really interesting. Arnaud has asked, why do we care about searching for the invisible in the universe?
Excellent. That's what I was waiting for. So one of the answers is very obvious. The first one is scientific curiosity, right? That is human curiosity. If because we know that 85% of the mass of the universe is missing and we only know 15%, then our scientific curious mind wants to know where is the rest, what is the rest, how the rest interact, right? So scientific curiosity is one of the primary motivations, and that is basically why it is called fundamental science, because it's not a science with an immediate application, but another answer to why we care is because it will help us to better understand the universe and its fate. So there are still some discussions, although it might not be among the scientific community, there's still some discussion about the age of the universe. Are we sure that the age of the universe is as we know it today, almost 14 billion years, right? And we know finding the amount of dark matter will help us to know what is actually the exact age of the universe. So let's say the dark matter we find end up to be more dark matter at the Big Bang compared to what we have estimated it to be. Then a universe that has more dark matter will be younger than the universe today. And a universe that has less dark matter will be older than the universe today. So knowing or finding dark matter will help us make sure that the age of the universe as we know it is indeed as we know it, and also help us understand the fate of the universe, as there is this balancing act between the dark matter and the dark energy in the expansion rate of the universe and so forth. And then the third reason that I like to think about is about potential technological advances, right? We know that all the technological advances we have made so far, and then we have made great progress in technology, is only using the numerous amount of particles of the standard model included in only 15% of the mass of the universe. So imagine then what we can do with potential particles in 85% of the mass of the universe. One of the examples I'm going to give to baffle this point is, for instance, at some point when we were looking for antimatter, people were asking, what is the practicality of antimatter? At the beginning, it was like a sort of fundamental science, but when we did discover antimatter, we started to use it then, for instance, in medical field for cancer therapy, like the PEP treatment for cancer therapy, right? So I think discovering dark matter will set up an avenue to study it, and then we'll be able to go from there, perhaps developing some technologies that we don't even have the imagination to start to think about right now. So those are the three different reasons for me why we should look for dark matter.
Yeah, I'm always like kind of intrigued by the you just don't know, like the potential technological advances. Like you just don't know until you find it. You don't even know what it can be done, right? And I think that's such an important point. There's another question that I think my helper is writing in, but I can't see it. So I'm gonna see if I can find it in the actual chat. I think it's from Edward. Given that dark matter is not part of the standard model's set of fundamental particles, would a confirmed dark matter particle observation overturn the standard model or just end up extending it?
Excellent question. So basically, confirming that dark matter particle exists will not overturn standard model particle, but we extend it. So what we do is basically change our mindset where we thought that standard model particle was a complete theory out there, like set and done. There's nothing to add, nothing to remove to it. But it will help us basically move the boundaries of standard model, understand that there are particles beyond the standard model. And I think even in the standard model particle, at some point we were thinking that the neutrinos were massless, right? So knowing that the neutrinos have mass was also a way to not change, not remove the standard model particle completely, but refine it. So dark matter particle, basically finding them will be a set of particles beyond the standard model that does not exclude the standard model, but refine it to be a more complete theory, basically. And on that note, there was some thought about dark matter particle may be a class of supersymmetric particles, which are basically like standard model particle but mirror image. What you see on the slide with standard model particle is reflected in that superposition between them. So we are still probing those supersymmetric particles to completely rule them, but we know that even if we were to rule that supersymmetric particle, we might still have a different class of particle for the dark matter that will again help to refine the standard model, but not excluded. So you just be beyond the standard model particle.
I guess that's a good thing, maybe. Although I do find in science it's really exciting when you have to throw a whole theory out, but it's nice that everything else that we've done kind of gets to stay and it gets to be extended.
Yeah, so like a comment about that. I remember when I was in high school in Cameroon, at that point, I thought neutrinos were massless, right? So when I traveled and I discovered that neutrinos have mass, although very tiny, close to zero, it's not zero. I was thinking, oh, does it mean that everything I know should be thrown away? No, right? Everything you know is just a building block and it gets refined with time. So yeah, standard model is a building block and then it gets refined with time. It's not going to be thrown away.
Like that. All right, we are out of time for questions, so I want to thank you so much. We're going to have you back, and I think we have a couple still questions left to go with you as well, so we'll bring that to the panel. But I want to thank you again for an excellent talk, and I can't wait to see you in a little bit. And so we're now on to round 2 of trivia, which of course, enable that, and sorry, PowerPoint is, you know, technology, it acts up, right? That's what makes it technology. So let's start sharing my screen, sorry. And so round 2. So remember, these go into the Google form that you have open. You can look in the YouTube description for that link and go ahead and put that in. And we're going to start off with some fun sci-fi reference, like we usually squeeze 1 or 2 of these in. And that is, what is this object or this location? Where is this picture taken? And we are going a little bit behind time, so we're going to go through these fairly quickly, but again, you'll see them all one more time. So question 7 is, this planet, which planet is it, inspired poets from early days and is known as both the morning star and the evening star. Which planet is it? Both the morning star and the evening star. Which planet is it? Which planet rotates on its side? Not right side up, not upside down. There is a planet that rotates upside down. Which planet rotates on its side? And you might have noticed a theme. We're very solar system focused this time. What is the common name of the star Alpha Ursa Minoris? What's the more common name of the star Alpha Ursa Minoris? And last but not least, what is the largest crater on Earth's moon? Also known as the moon. What is the largest crater on Earth's moon? Okay, last time, we're going to go through all the questions just one more time. Name this object. Where is this location or this object? Question number 7 is, this planet inspired poets from early days and is known as both the morning star and the evening star. Which planet is it? Question number 8, which planet rotates on its side? Has very, very long winters and summers. What is the common name of the star Alpha Ursa Minoris? This is question number 9. What is the common name of the star Alpha Ursa Minoris? Alpha, if you didn't know this, stars are named according to how bright they are in the constellation. So Alpha means it is the brightest star in the constellation. Alpha Ursa Minoris. And last but not least, definitely I think one of the hardest questions of the night. What is the largest crater on Earth's moon? All right, and that concludes trivia. So I'm just seeing it's at almost 8:15, so we will accept responses until about 8:15. So make sure you get them in if you want to be included in the prize for the highest score. Of course, everybody will still be available to win the, as I think Sean called it, the participation trophy. There will be a prize for just a randomly selected person as well that submits the trivia. But without any more ado, I want to go on to our very last speaker. So Stéphane, if you want to maybe show your video, our final speaker tonight is Professor Stéphane Courteau. He is long overdue, in fact. He was on this call in October to speak, and he just never got a turn. We ran out of time. And so he is now here after a long wait. And I know he's very eager to speak on this subject. And so Stéphane is a professor in the Department of Physics and Astronomy at Queen's University. He's been here since 2004. Stéphane studies the structure, evolution, and dynamics of evolved galaxies, as well as the interplay of baryons and dark matter in the universe. Stéphane has a keen interest in outreach and has been the Queen's Observatory director since the International Year of Astronomy in 2009, marking 400 years since a certain picture of a man that we saw earlier today used a telescope to look at the sky. A little bit of history on Stéphane. He did his PhD in 1992 with Sandra Faber at UC Santa Cruz with Lick Observatory, looking at the cosmic velocity fields. He was an NSERC fellow at Cornell University from 1992 to 1993, an NOAO fellow at the Kitt Peak National Observatory in Tucson. Good old fellow, likes to spend some time in Arizona like myself. And he was also a research associate from 1996 to 1999 and a Plaska Fellow at the Herzberg Institute of Astrophysics in Victoria. And then you were, I don't have it here, I didn't copy it over, you were a professor at UBC, or was it, yeah, UBC, before then coming here in 2004 and becoming a full professor in the early teens, 2012, I think. And so today you are giving us a talk on Vera Rubin and her telescope. I'm very excited for yet another facility that is soon going to be doing some amazing science. So Stéphane, I'm very much looking forward to hearing your talk tonight.
All right, may I share my presentation? Okay, we're going to do this and let's hope that it all works. Come on, what do you see?
I don't see anything right now.
Nothing yet. That's perhaps because the share button, share, this dot to share. And hold on, a nice picture in the background here, but I think really what we want is this, right? We're good to go? Mark, you forgot to say a number of things. Perhaps the most important one is that I gave the very first Astronomy on Tap presentation. You recall, that was in Kingston on the equinox of 2019, March 21st, 2019. Those of you, and I know there are a few on this call present, will recall that it was a remarkable evening in more ways than one. So this glass right here is a happy reminder of the noisy pub where the event took place. So, all right, today I want to tell you about a unique, let me make sure, yeah, a unique US-led project that should see first light sometime this year, that really will start producing real science next year. That's the, as Mark was saying, that's the Vera C. Rubin Observatory. Now that I've said the official name, I'm going to call it the Rubin Observatory. Oh, and it just happens that I'm wearing my nice Rubin Observatory shirt just for this occasion as well. Right, so a disclaimer as well before I start. Despite the fact that I'm bestowed with these beautiful outfits, I am not an official representative of the Rubin Observatory. I chose this topic out of sheer interest, okay? But also because, as you'll see of some personal connections, you'll understand why I think it's appropriate now to talk about the Rubin Observatory. Anyway, we'll get to that shortly. You know, Mark talked about the JWST, the James Webb Space Telescope that launched last Christmas. And very much like Webb, this machine here, Rubin, is likely to revolutionize astrophysics. And I want to explain why. In just a few years, we all want, but especially I think the students listening to this presentation, want to be prepared for the onslaught, to use Nick's word, of data, the unprecedented floodgate of LSST data, that once again will revolutionize astrophysics. I would like to start with this overall view that shows the aperture of most of the most important telescopes since 1900, almost the previous century. I would love to tell you stories about almost each and every one of them. We don't have time. I'll just mention a couple. This one here, the 100-inch telescope, so-called Hooker telescope that Edwin Hubble used in the 1920s to discover ultimately the expansion of the universe. Perhaps some will say the greatest scientific discovery of all times. That was in 1929. And the telescope is located very close to where Alvine is working now. Alvine's at UCLA, and if she looks up, perhaps out of her window, she can see, you know what, maybe not from UCLA. It's a little far, but if you go to Pasadena, you can see Mount Wilson in the back. Back then, it was a fairly dark site. Not too far from Mount Wilson is Mount Palomar. So you see the little ring, the donut here. It had the largest telescope in the world for the better part of 50 years, called the 200-inch telescope. It was used in part by people like Martin Schmidt and Alan Sandage in the mid-60s to discover this new class of objects that we call AGNs, active galactic nuclei, which are really the result of supermassive black holes and galaxies. Rubin will be extremely important in mapping the time evolution of these AGNs. There's so many other telescopes. As I said, I'd like to tell you stories about them. I'll just point out two different classes. There's these large monolithic mirrors, fairly thin monolithic mirrors that extend in diameter over 6 to 8 meters. We Canadians in particular have access to the Gemini North and South telescopes. In the north is in Hawaii, the south is in Chile, Subaru's in Hawaii, Keck here. These actually different technology. These are segmented mirrors. And you see there are many other segmented mirrors that have been constructed. Perhaps now the most famous one is this one down here. I'm not sure how much you can see on your screen. This here is the 6.5 meter James Webb Space Telescope that's now operating in space. And by the way, as Mark said earlier, doing great. We can expect great results from Webb. LSST and Webb, as I said, will bring a revolution in astronomy. LSST for various, not LSST, sorry, James Webb for its own reasons that I won't discuss now, but LSST, or actually, I need to step back. There's three names that we want to be familiar with. The Rubin Observatory, which will conduct a survey that we will call LSST. I'll explain the acronym in a second. And the telescope itself also has a different name. So the acronym LSST is for a 10-year legacy survey of space and time, okay? It will produce an extraordinary amount of data. I'll come back to that shortly. The main science areas are probing dark energy, dark matter, cataloging the solar system, exploring transient phenomena in the sky. I've meant examples of transient phenomena, AGNs, supernovae, colliding neutron stars, colliding black holes. I'm missing a few, but electromagnetic counterpart of gravitational waves, there are many, and Rubin will make a difference. Mapping the Milky Way for the familiar ones on the call here, this telescope will do a better job than all of the other satellites that have mapped the Milky Way before, including Gaia. I move on. I tried to click here. There we go. So, you know, big projects like that, I will come back with the science that's going to be produced by the telescope somewhat briefly. First, let's look at some cool pictures. You know, large projects like this one never happen overnight. Typically, big projects like James Webb, like in fact the telescopes, the underground telescopes that Alvine was talking about, and that we operate here at Snow Lab, all this massive instrumentation requires decades of planning. And Rubin was about 30 years in the making. In the 1990s, two astronomers, Roger Angel and Tony Tyson, dreamed up this so-called dark matter telescope. And over time, the project quickly won approvals with various administration levels. And next thing you know, here in 2011, Cerro Pachon in Chile was blasted. And about 10 years later, you have, you know, a structure that's almost ready for first light. In fact, this picture here shows you Rubin last month in January, 2 months ago in January. Okay, so all we need now is, as you'll see, a couple more fixes, and in probably like 6 months, we should see first light. I like this picture here of the primary mirror. It's in fact both the primary and tertiary at the same time. I'll explain why in a second. It used a special technique. It's called spin casting, where the glass is heated in an oven that spins, and a glass acquires a certain curvature. You cool it down and you get these very lightweight, huge mirrors. The next picture shows, I like this one, it's kind of cool. I don't know how much you can see on your screen. You see people checking whether the encasing is going to clear. You know, we have centimeters here passing through the Peclaro Dam, which is just below Cerro Pachon. Next slide shows the mirror being wheeled up the mountain all the way up to its location. Next, you see the Gemini South telescope, and this is the so-called SOAR telescope. Well, here's a nice picture of the telescope being built, nearing completion. So as I told you before, the observatory is called Rubin, the survey is the LSST. The telescope itself is named after Charles Simonyi, who donated, the multi-billion, the Microsoft builder with Bill Gates, multi-billionaire, donated a good chunk of money for this project. I'll return to the telescope in a second, but now you see the full observatory, and notice, I don't know if you can see this little one in the back. It houses a 1.2 meter auxiliary telescope that's going to be used to provide measurements of atmospheric conditions on a regular basis and give the proper calibration for LSST data. So while the Simonyi telescope is pointing in some directions, this calibration telescope will strictly look at standard stars to make sure that the photometry is properly calibrated. And so now we look at this. I love this map here, cross-section of the telescope. You've seen pictures of it. And now you can start to appreciate why it was built that way. Every once in a while, typically once a year, you need to recoat or aluminize mirrors because they oxidize over time. You see the coating chamber here that's lying in this room. So the mirror will be elevated down to this room. Telescope will be operated from the rooms below. Some cool statistics about the telescope. It's heavy, 300 tons, and yet, and this is what makes it so special, it's going to be able to slew 90 degrees in 9 seconds, 10 degrees per second. That's crazy. Mind you, it's compact, and its structure allows it to do it. It'll take deep images every 15 seconds, and I could explain later. The 15 seconds is basically a compromise between spotting both the faint and moving sources. You may ask questions afterwards. I think I'm running out of time a little bit. Very quickly again, both the telescope is amazing. The camera itself is the largest of its kind and certainly the most expensive, $170 million ever made. It's an extremely fast camera as we need in order to see faint objects in the solar system in particular. I could go over the optical design if people want to. I'll just point out the technical spec here that it's a very, very fast focal length. And the telescope will survey the entire sky in only 3 nights. Every 3 nights, Rubin will resurvey the sky. And that's how we can, with proper cadence, track evolving, track the universe ultimately in real time. The detector itself is the largest as well ever built. These numbers are staggering. 189 4K by 4K CCDs. Okay, largest camera again ever built. And the incredible thing for those of us who've used telescopes before, all these CCDs will be read in 2 seconds. It's amazing. I'll return to that if you'd like. Some very quick facts. The field of view, it is not shown here, is 3.6 degrees. So that means you can squeeze 7 moons or across the 60,000 pixels of the camera and possibly even 40 moons in the entire field of view. Its resolution, which is 0.2 arcseconds per pixel, is so good that you could spot a golf ball from 24 kilometers away, okay? Exposure times will be 15 seconds. The 3 nights is what's needed for an all-sky imaging. I mentioned the F ratio. This is an interesting statistic here. Any part of the sky will be surveyed at the end of the 10-year survey 800 times. This is equivalent over the course of those 10 years to staring at a patch of the sky for an entire night, roughly. Interesting coincidence that way. Every night will produce 15 terabytes of data for a total of 50 10 to the 15 petabytes at the end of the project. That's only in data, 500 petabytes in data products. That's wonderful. I will skip all the really juicy, cool information here. Perhaps only mention that we have wavelength coverage that goes from the UV to the near infrared. And at the end of the survey, Rubin will have mapped 20 billion galaxies, 17 billion resolved stars in our Milky Way, 7 million orbits of solar system bodies. And this here, we can discuss the average number of alerts per night. That's about, and one more before is this, it's technical a little bit, but for the aficionados here, this parallax uncertainty of 1 milli-arcsecond over the course of the entire survey. This means that we can do extremely accurate positioning of objects, and that is in fact one of the missions of Rubin, of the Rubin telescope. I will use maybe another minute and a half if the organizers allow me to explain why this telescope has been named after Vera Rubin. So Vera Rubin is very much an astronomer extraordinaire. I should be able to say extraordinaire without any problem. And so, by the way, should the other 2 speakers. That's a nice common denominator of tonight's speaker roster. So she pioneered studies of galaxy rotation rates, which later were used, as Alvine said in her talk, to infer the presence of dark matter in galaxies. She studied with giants of physics, some of my heroes, Hans Bethe, Phil Morrison, Richard Feynman, George Gamow, and she then herself became one of my scientific heroes. She has made very important scientific discoveries, very much like Alvine as well. She is a strong advocate for STEM, and in particular in her case, back then, we're talking about the 1950s, 60s, focusing on women in science, and she has shown tremendous mentorship in training female astronomers. Okay, quote, there's no problem in science that cannot be solved by a man, or that can be solved by a man that cannot be solved by a woman. Way to go, Vera. What's my connection there? Well, as part of the International Year of Astronomy in 2009, I organized this conference here on galaxy masses and dark matter. You know, it was really an excuse to celebrate the career, to, you know, Vera Rubin's career, which surprisingly had never been done before, and sadly would never be done again until she passed on December 25th, 2016. You see Vera here in the middle with myself and the co-organizer, Olaf de Jong. And then the very direct connection between me and Vera is the fact that Vera trained my PhD advisor, Sandra Faber, and Sandra Faber's advisor was Vera Rubin. Therefore, you follow that Vera was my scientific grandmother. I've never published with Vera. She was a good friend. We had many discussions. I visited her many times at the Carnegie Institution in Washington. We met at conferences. We observed together at Palomar Observatory, but again, never wrote a paper together. We yet did very similar research. Perhaps my greatest claim to fame is a kiss on the cheek from Vera in 2009. I haven't forgotten this one. Last but not least, the continuation of this mentorship from Vera to Sandra Faber, my supervisor, and myself, is some of my former students. This picture was taken in 2009. And I'm particularly happy that two of my former students, Jonathan Sick here and Lauren MacArthur, are directly involved in the LSST project. And in closing also, I should point out that Lauren was supervised by Tony Noble when she was an undergraduate student at Snow Lab. That's it for now. Maybe in 2023, 2024, I'll return and give you a more scientific overview of the latest results that will come from the Vera C. Rubin Observatory. Thank you very much.
Thanks, Stéphane. It was fabulous to be able to hear you give an Astronomy on Tap talk for once. Because
you didn't hear one in 2019?
I don't think I heard one in 2019.
That's right. You don't remember you don't remember that extremely memorable event.
I mean, it was very memorable. I'll give it that. And I know that there are actually people here that were people in the audience that were there at that night. And I'm very sorry that you were the first to give the talk that night. And so we still were fixing some audio issues and some etiquette issues. And so we were better able to hear the next two speakers. But you took the bullet for the rest of the night. And so I'm really, really happy to have been able to hear from you. My interpretation is because you've been here twice but weren't heard the first time, you thought you could speak for twice the length. And so there might not be a lot of time for questions.
I don't think so.
You spoke for 18 minutes. It's cool. But I do have some questions. And so the first one is actually noting, so in your plot of all the different telescope dishes,
okay,
well, you have the Vera Rubin telescope. It's I'm actually forgetting now the name of the actual telescope. It has a very different shape. Now, what you revealed was that it's because the primary is itself the tertiary. And so I'm a little bit curious why that's the design that they went with. And there's a question in the chat that was the same question. Right.
So here we see in the middle again, this ring-like structure. Note that they're all ring-like, right? So it very much depends. As you mentioned, Mark, it's, if the secondary is big, then it blocks the view of the. So the reason for this is there's a requirement here that the camera be fast. Okay, so the focal length or the f ratio, which is the ratio of the focal length to the aperture, needs to be close to 1. And so the faster the telescope, the more energy is deposited per pixel. What that means then, so for people who do photography here, they know that if you buy a big lens, of course, you're gonna pay a lot of money for it, but it also means that you're capturing a lot of photons in your lens, and you can shoot faster. So, for instance, if you do wildlife photography, you want the biggest possible lens. Well, the wildlife here is faint objects in the sky. And in particular, when we look at the solar system with object, asteroids and near Earth object, they move fast and they're faint. So that means we need to catch their light very quickly. Okay, so the design, even though we are losing a little bit of the primary mirror, the effective radius based on the collecting area of the telescope is still 6.4 meters, which is huge. Mm-hmm. Okay, and then you look basically at the properties of the image, and again, how concentrated the beam is per pixel. And this telescope, of all of them that you see on this screen right here, is the fastest ever produced. And that's why it has this very interesting ring light design. For the aficionados on the call, all these telescopes here have typical focal ratios of f20, f14, f15, f20. And the reason for this is that you can stare. The bigger the telescopes typically are meant to study the push, the envelope, to study the universe to its edge. Those objects are very, very faint, and you want to sit on them for hours. And so the focal length there, the long focal length allows you to, I said something wrong here. I'm going to backtrack. Okay. With the faint objects, you still want a fast lens. You want a fast telescope because they're faint. When you can afford resolving structures because they're bright, then you want to go with a long focal ratio. So that's why most of the telescopes here have f15, f20. Many of the objects are in a decent brightness bracket, but you want to resolve them spatially, and that's why you want basically a telescope of that focal length. That's not the purpose for the Rubin. Rubin is meant to observe objects that'll move fast in the sky. So I mentioned the 15 seconds. That again is a compromise. You have a short or fast telescope, if you wish, with f1, f1.2. And you also have some only 15-second exposure. You might say, well, why not go for a minute, 2 minutes, 3 minutes to go deeper? Well, already Rubin will go very deep, and in part because images will be stacked and then blinked to see if there's variations in its luminosity. But if you were to use a somewhat longer exposure time, you'd miss those fast objects in the solar system. So compromise between speed and the desire to catch faint objects. So that's what gives you this crazy design. And this, I didn't have time to talk about the camera, which is spectacular. I mentioned the camera, just the camera alone is $150 million. The largest, just the secondary mirror is the largest of its kind ever made. All of that with the intent of making this telescope fast.
So I think there's maybe time for just one more question, but we're going to have you back for the panel where there'll be more questions for you, just to give people, I know people are just so excited to hear the answers to the trivia. So I want to bring that in before bringing you back. Is if size of material was not an issue, with 150 million, let's go bigger, let's go whatever. What is the ideal setup for a telescope? Should there be lots of just little ones? Like, is that the better way to go? Is it more medium size or circle, hexagon shapes? Like, what's the dream? What's the ideal?
Well, I think the dream, you're looking at it, and I'm not alluding to your speaker. I'm talking about I'm talking about the slide that's shown on the screen here. What you need is a combination. Already we know, so the Rubin Observatory, I don't know if you followed, it's strictly a photometry telescope. It's not going to do spectroscopy, which, by the way, is surprising because Vera Rubin made a career with spectroscopy, but that's another issue. So telescopes complement each other. You see here the ELT, extremely large telescope, that's going to be built. It's almost 40 meters in diameter. It should be finished in a couple of years from now, also in Chile. And its purpose will be to drill through the cosmos to see the very first galaxies at the very first, at the beginning of time almost. Very few telescopes like Rubin had, and in fact, none have the ability to do synoptic time cadence on for measuring the variability of cosmic sources. So Rubin has this very specific mission to map the entire universe, or at least as visible, the entire sky, I should say. Let's be careful. The entire sky, not universe, visible from Chile, okay? And that's never been done. But the other ones here, like James Webb, fulfills a completely different niche. As you know, it's outside the atmosphere, so it's not subject to fluctuations. And so it will get very crisp images, which ideally will provide some information, as you said, Mark, on life on other planets. These measurements, require extremely high spatial resolution. They're all complementary of each other. I don't know if you notice here at the bottom, there's this gray zone for radio telescopes. You have Arecibo, you have the FAST telescope in China, just 0.5 kilometer in diameter. Those are needed as well. These, by the way, only study the optical regime, right? So we also need UV telescopes, infrared telescope, X-ray, gamma ray, and so on. So the answer is
having a drink for Arecibo, if that's okay.
Okay, let's drink to Arecibo. But the bottom line here is you need a suite. You need all of them. But Rubin fills a niche that didn't exist before. And so we could talk, especially following Alvine's talk, we could talk about dark matter and what Rubin will do for dark energy, dark matter, transient surveys, and blah, blah, blah. That'll come in a talk maybe in 2023, 24 again. Okay, when we have results.
I'm seeing just a very last quick question. I'm seeing overwhelmingly large telescope, because astronomers are really creative in naming some of these things until eventually canceled. So obviously that is a huge primary. Would something like that, do you think, ever be built?
I could. I mean, look, the idea of segmented mirrors is really to just put together small 1 meter hexagonal telescopes. So why not? I don't think so. And especially, I hate to say with the current, this would be a long discussion. Current climate, I don't think, if we manage to build the ELT, not EE, but the ELT, this one is looking good. The TMT, there are political issues in Hawaii. If we can get those two going, we'll be very happy. I would be extremely surprised if I see an owl. This is how the overwhelmingly large telescope is called. I don't think I'm going to see that in my lifetime. I don't think we'll need it, actually. But I'd be happy.
Sounds like a different conversation.
It's a different conversation. Yeah.
All right. Well, thank you so much for a great talk. And it was great getting to ask you these questions. And we'll see you back in just a few minutes. Okay. So thanks again. Take care. And so now I would like to get time for the reveal. Share my screen. And I think everybody can see that. So we've had 2 rounds of trivia. You should be able to see that now. And I will say, make sure you submit your form. Make sure at the very bottom you submit it before right now, because as I do the answers, we're going to do the cutoff. We'll no longer accept opportunities to learn, to guess these questions. And so it's time to find out what the answers are. So let's remind ourselves, question 1 from round 1, which is larger, Neptune or Saturn? The answer is Saturn, even if you don't count the rings. Even the planet itself, without the rings, is bigger. I think I need to mute Stéphane. There we go. Question number 2. Where is the Oort cloud located? This is not a cloud on Venus, although that's a pretty convincing answer. In fact, it is a cloud of rocky, icy bodies that extend beyond that of Pluto, beyond even the Kuiper Belt, which is where Pluto is found. The Oort cloud is found even further out. And it is, a really, really neat place that extends very, very far from the sun. What is the sun's outermost atmosphere called? Well, I'm certainly drinking the exact opposite color. That would be a corona. But hey, another cheers to Arizona tonight, which is where we used to drink corona a lot. But the very, very hot atmosphere is actually like millions of degrees around the outer edge of the sun, the outer atmosphere. Very, very hot, but very, very diffuse, very low density. And it is the corona. Name the scientist. Well, that is a picture of Galileo Galilei, and taken probably around 400 years ago. What is the farthest distance from Earth a manned mission has traveled, plus or minus 20,000 kilometers? I think we'll accept a half a point if you just said the moon, roughly. And that's because the answer is actually Apollo 13. On April 11, 1970, went about 400,000 kilometers, which is actually far side of the moon, even farther than, say, Apollo. I think Apollo 10 also orbited the moon. But Apollo 13 was the furthest mission to go from the Earth. And I'm hearing, for those in the US, I know Fred is here from Connecticut. It's about 250,000 miles in those other units. Trivia round 2. So we started with this naming this object. This is, of course, the bridge of the Enterprise D. We'll accept just the Enterprise, but it's the bridge of the Enterprise in Star Trek Next Generation. This planet inspired poets from early days and is known as both the morning star and the evening star. Which planet is it? Well, that would be Venus. Venus is a wonderful planet to see, either depending on which side of the sun it is with respect to our position in the orbit around our sun. You will see it late at night or late during the day, just around sunset. You'll see that kind of a setting, really bright star, or unlike me, if you're somebody that gets up early, we've already had this conversation, maybe you can see it in the morning when it's on the other side of the sun, rising shortly before the sun does. Question number 8, which planet rotates on its side? Well, that would be Uranus. It's a fascinating planet. Venus basically orbits upside down, rotates upside down. Uranus is basically bang on its side. We think it's from some kind of early collision in the early solar system. Maybe Arnaud could speak a little bit about maybe planetary collisions, I'm not sure. But yeah, Uranus is a really funny story there, and it rotates on its side. Question number 9, what is the common name of the star Alpha Ursa Minoris? This is, as I said, the brightest star in the Ursa Minor constellation. And so if that wasn't a big enough hint, it is the North Star, or Polaris. And last but not least, what is the largest crater on Earth's moon? My go-to would have been like Tycho, but apparently it is the South Pole Aitken Basin. It's a very, very large crater, and I believe that might be one of these craters that could actually have water ice deep in the shade at the bottom of the crater. And so that's it. That's the answers to our trivia. And we are running a little bit late, so I really appreciate everybody that's still hanging out with us. I do want to give one opportunity to maybe ask a few questions of our panel just to end the night and thank everybody again. So I encourage all of the panelists to turn on their cameras and join me while maybe I have a chance to first, I think most importantly, is just invite if any of you guys have questions for each other. But thank you so much for contributing to your talks tonight. It was a really, really fun conversation with each of you.
Well, apologies for my fellow lecturers that I went on so long. Sorry.
I should say that you weren't the only one. We all went, and I even went longer with some questions. So I think it was not you. You do not own sole blame on this, Stéphane. So
I share the blame. So perhaps I can start. I had a question about the data from the Rubin telescope. Is it going to be publicly available, or is it going to be only for the people signing up for some time on the telescope?
It's the latter, right? So the proprietary period will be 2 years if you're a member. And so there are, in fact, Canadian, well, you're at UCLA, I'm sure there are people at UCLA who will have access to this. There are only a few Canadians, actually. But yes, 2 years is the proprietary period. One really cool statistic that I didn't mention because I was so grossly out of time. Did you know that when the data are taken, which is again 15 seconds of exposure, as soon as it's taken, which is a 2-second readout, which is baffling, in 5 minutes, it's going to be in the States. Max. And then within about 60 minutes max, they will be able to do all the cross correlation with previous images to see if there's transient phenomena happening. So there's going to be 3 data collection centers, one in Chile, in Santiago, in La Serena, sorry, the other one in Tucson, and one in France. And all these centers will analyze the data instantly to see if they're transients. Anyway, the bottom line of your question is you need to be a member. So for instance, I'm not. That's what I meant in my very first disclaimer. I'm close to it. You saw my different connections. It'll be very, very tempting to knock at people's doors, but that's not how it works. And I'll just wait, like everyone, for my 2 years to use the data.
Excellent. Thank you.
Your answer did make me want to ask a bit of a follow-up, which is, first, how big is a single image that the data can be transferred in 5 minutes up to the States? And there was a follow-up question, which maybe I'll remember by the time you answer that last one.
The image is going to be 60. Each image is not too big. It's 60 gigabytes.
Okay. Yeah, right. Not too bad.
No.
And you answered it too quick. I can't quite remember what my other question was, but maybe it'll come back to me if it's important.
All right.
Yeah, is there any other questions here? Or I do have some leftover questions from each of your sessions because I cut them a bit short. So, but yeah, I don't know, Arnaud or Stéphane, do you guys have a question for somebody else?
No, I'm good.
Okay. Well, I was a little bit curious, Arnaud, as you're kind of getting the data of the different exoplanets and the disks, that are kind of the precursor to the planet systems, what kind of system, exoplanet, or these disks, these amazing, frisbees with gaps and whatnot? I'm curious to know, like, do you have a favorite? Is there particular characteristics that really capture your attention, interest, or imagination?
I think everyone is very biased towards the ones that have gaps and rings because they're intrinsically immediately interesting. But on a recent research project, I had a real appreciation for the very tiny compact ones where there are no rings. They're not huge. There may be only 5 or 10 times the distance between us and the sun, so 1 AU. So they're quite small, and in that case, it really poses some difficult questions as to whether or not you can make planets in something that's very small. So I think those would be like my favorite class, I guess, of like short, small, compact disks. But for research purposes, those are really hard to look at. So I like the big ones for research purposes where it's a lot easier to do science.
Yeah. And Alvine, I mean, it's a question I was thinking about was, what is and this is a question that came up too when you were talking a little bit about the shielding, which is just what is, like, are all shieldings made the same? Is there different types of shielding that should be used for different research projects? Or, what material is used typically in that third phase that you need to put into that hunt? What do you do for shielding? What material can that be?
Excellent question. So, talking about shielding, you have to ask yourself, what do you shield against, right? Because shielding, you are trying to stop some type of particle from coming into the core of your detector. So if you are shielding against Newton, for instance, which actual background that would exactly mimic a dark matter signal in your detector. What you want to do, going back to that BYOB board game, is to use a shielding material that has the same mass as the neutron, because you know, as with the BYOB board game, that the maximum energy transfer happens when the incident particle has the same mass as the target particle. So what material has the same atomic mass as the neutron? We have water, right? Because water has proton, and then the proton atomic mass is the same as the neutron atomic mass. So to shield against neutron, then we have huge water tank around the detector. So those do shield against neutron, and also they help shielding against gamma particle. Now, once you have that neutron shielding, you will try also to shield against gamma. Though the water shield a little bit against gamma, having an extra layer, for instance, of lead material, because it's very dense, it will help the gamma particle to quickly lose their energy. So an ideal shielding has to be first designed to mitigate against the particle you want to mitigate against it, and second, be hermetic. So no air gap in between, because if there's a gap in between, then the particle can go through the gap and then hit the core of the detector. Some people prefer then, in that case, having a sort of spherical shielding as the one that NewsD has designed, because a spherical shielding has the same thickness of shielding around the detector, no matter the angle at which you are looking at. Some other particle prefer to have like a cylindrical shielding, like the one we have in use in LZ right now, because you know that having a cylindrical shielding, maybe the background you are focusing on is coming from the wall of the laboratory, and the ceiling is quite high compared to where your detector is located. So you are mainly concerned about the wall of the laboratory. So you have this cylindrical shielding that will shield against neutron coming from those wall and gammas coming from those wall. It depends. But the most common materials used in any dark matter detector are either water or any hydrogen material like PTFE and so forth, or lead to shield against gamma. And also one complexity that we sometimes add to the shield instrumentum, having some light detector instance inside the shielding, such that we can, if we don't succeed in stopping the particle that goes through the shielding, we succeed in tagging that particle, such that if that particle passes the shielding and interacts the detector because it was tagged, it can still be removed via some analysis that will, for instance, study the timing the particle left the shielding to enter inside the core of the detector to remove it from the data. And then, because of the sake of time, I won't keep on going. So shielding depends on the material, on the particle you are trying to shield against, and the common particles are neutron and gammas. And to shield against them, you use water or any hydrogen rich material and lead.
It sounds really, really interesting, and I think it's its own whole study, I think, of focusing on just how to solve the shielding problem. Thank you for that. Arnaud, there's a question for you from Tony. Maybe I missed it, he says, but if the dust is all sand, like you said, silicates and carbon, why are the planets such different compositions? Shouldn't they all just be sand balls?
Actually, I made a mistake. There's also a lot of ice around the sand. So that's a good catch. It's not just sand, there's also ice. And so ice of a variety of species, from water ice to like carbon, oxygen, like CO ice, and then more complicated ice, like molecules, then to varying degrees of like proportions. But yes, at the end of the day, though, our planets are significantly silicate rich. When you think of the Earth, like we've got a molten iron core, but then the rest of it, until pretty much the crust, is mainly a silicate rich like mix with some magnesium mixed in there and some calcium. But yeah, it's quite biased, I guess. And carbon rich. Sorry, and carbon.
Right. Yeah. Yeah, I guess the water water is a pretty big component. I know that the comments and whatnot still have a lot of that water even today. That I know that there's like actually, yeah, I don't want to go there, but you know, the comments that we've now investigated and been able to land on, it's lots of interesting studies coming out from that to understand some of the kind of primordial water that made up the solar system. I think a last question I wanted to go to Stéphane, and he has a hand up, so I think he has his own question first. Let's start with that.
It's not so much a question, it's a correction. You know, like, you know, I need to correct myself. I think in my dyslexia, when I answered Alvine's question, it's not 5 minutes that it's going to go from Chile to Tucson. It's 5 seconds. You know, 5 minutes. 5 minutes would be ridiculously sluggish, you know. So they're using redundant, you know, I think it's 100 gigabyte per second links, and it's going to be 5 seconds to go from Chile to Tucson, and in 60 seconds they will then know if there was anything transient that requires breaking the cadence and perhaps following up. Anyway, I wanted to clarify for us, for everyone who's listening, not 5 minutes. No.
Thank you for the clarification.
I think an important thing that you're also highlighting there, Stéphane, is the role that computers are playing in being able to deal with any of this data so that it can be useful. It's just coming in at such a rate that
I didn't have time to talk about it. I focused today very much on equipment, just actually pretty pictures and equipment. But I mentioned the work of, say, my two former students, Jonathan Sick, Lauren MacArthur. They're strictly doing data management. The problems involved in managing such a large database are staggering, and they're still being worked on. You know, so you're right, Mark. This is a big. I mentioned it at the beginning. There's the equipment, the data management, as well as the outreach component. It's a very exciting set of components that all make up the Rubin Observatory.
Now, Stéphane, I'm going to give the last question I have to you as a way of kind of tying everything together.
I don't deserve it.
Oh, but Arnaud's raising his hands.
I have a question for you, Stéphane. I know, so you mentioned you're not on the LSST like science team, but with the data that will come in for your research, what are you particularly excited about? Like one thing.
Right. Oh, that's a big one. And I wish Nick could participate in this. So for those people who don't, Nick is also working with me. I mentioned that LSST is a strictly photometry operation, right? Survey. So that's great. However, for my, so it's going to be extremely important for dark energy, for instance. Okay, so I do cosmology. So dark energy, dark matter, topics that we discussed tonight. I'm not a solar system expert, and I understand from the purpose of just doing planetary science and solar system, it's going to be fantastic, but I'm not going to exploit those data. So dark energy, you can imagine with photometry, you will have lots of lensing studies, weak and strong lensing, and not to go into details, but baryonic oscillations, acoustic oscillations, but that's kind of where it ends. So for dark energy, it's fabulous. For dark matter, maybe less so, right? So for dark matter, again, lensing, and I'll be doing some of that, but I'll want to couple all the photometry with spectroscopy. And this is why, especially as a Canadian, I need TMT. And it's always been planned that way, that you need a very deep spectrograph to complement going with Mark's question earlier, LSST. So that's what I'll be wanting to do, perhaps develop surveys that complement LSST with the images that are going to be very, very deep. Oh, I don't want to go into details, but there's so much that I will want to do. Profile decompositions of galaxies, whether they're built with stellar halos that we cannot see right now, but LSST will, because it'll go deeper. Lots of things I want to do, but I'm going to have a little bit of time to think about it, because all the software is going to be put in place for this period of 2 years again, where I cannot really touch the data, and then I can plan, and when it comes, I can hit the ground running. Does that answer your question, Mark?
Yeah.
I said Mark, you know, but I know also Arnaud, but was that your question, Mark?
That wasn't mine, it was Arnaud's.
No, I know, but maybe he asked the same question. Maybe he scooped you.
No, my question was going to be, and it really needs to be maybe a quick one, is an opportunity for you to speak a little bit about LSST's maybe impact on either dark matter research or protoplanetary disk research. And then,
Right,
so
right.
I think we just need another hour.
I know it would take time. So we will have another presentation like this. This really deserves LSST, Euclid. Arnaud talked about the Roman telescope as well. James Webb. It's going to be good to have discussions of that sort a year or two from now. I must say, being a student right now, like putting my, for Arnaud, Nick, and all of you listening to this call, it's just an incredibly exciting time, right? So my closing statement is, some bad things happened in Ukraine just in recent hours. Let's forget all these divisions and let's focus on the beauty that we have as a race, all together, study the universe, but also pay attention to what's happening on Earth. But astrophysics is an incredible science to pursue. If I were advising a young student, I'd say, absolutely, you got to go for it. The facilities will be tremendous. Discoveries in the next decade will be incredible. I just want to get rid of, let's move on. Wars are stupid. They don't solve anything. So I'm a little frustrated. I'm in that mode as well right now. I'm sorry, guys.
Yeah.
But once again, these incredible projects that are happening in astrophysics are going to be a beautiful, wonderful revolution in the next decade. Let's close with that.
Yeah. Well, thank you again, everybody, for the talks you gave tonight, for the time you spent with us. Thank you to everybody at home joining in and bringing your questions. And I think there's like 10 likes and then all the trivia. We will be in touch with those that we select to win. So keep an eye out for your email. Hopefully you put in a way for us to contact you in the trivia form. And have a great night. Stay safe, and we'll see you again maybe in June. I hope to see you online and in person. So take care. Goodbye.